Welcome to another tech tip video where today we're going to look at how to create gears inside of Solidworks. In a previous video I show how to use path and gear mates to generate the motion in this gear train assembly, but that inevitably leads to the question, how do you create the gears themselves? And that's what we're going to do. We're going to show how to create both spur and helical gears. To get started, I'm going to choose one of my part templates, in this case a metric template. And I should point out we will be designing our gear using the metric module system, although you could just as easily create a gear using diametral pitch in the ANSI system, although some of the equations will be slightly different, if not reversed in some cases. Oftentimes when you start a gear, you know at least a few of the values you'll be working with, whether it's the distance between centers, the gear ratio or number of teeth, or the diametral pitch, or the module in our case. And in this case, we want to create a 2mm module gear with 25 teeth. So it makes sense to capture this information early on. And global variables are a great way to do this in SolidWorks. To add a global variable, we do this to the equations of the file. Although you'll notice the equations folder currently isn't visible because no equations have been added to this file yet. In any file, you can access any feature tree items that are currently hidden by right mouse clicking on the component icon, going to Hidden Tree Items, and in our case choosing Equations in the Equation Manager. Now, to capture a global variable, we'll go to the Global Variable section and give it a name, in this case Module. You'll notice the text is initially red, and this is because global variables need to be encapsulated by quotes, although pressing the Tab key will automatically add these in this case. We're going to enter the module value I previously mentioned of 2mm. You'll notice you can use the value 2, but entering mm will allow you to specify the units. This is great if you want to work with multiple units, such as centimeters, meters, or even inches and feet in this case, and work with multiple types of units. We also wanted to capture the number of teeth in this case. And we're going to, in this case, enter the value 25. Notice it is an integer value, so we're not going to enter the units behind it. When we go ahead and press OK, we will see that the equations folder now appears in the feature manager tree, and when we expand it, we can see the global variables that we've created. So we have everything we need to get started, but I should point out you could add other equations here. You could immediately solve for the pitch diameter, the outside diameter, the base circle, the root diameter, etc. But we're going to do that when we draw our sketches. So let's start that. Let's create a sketch on the front plane by selecting it and choosing Sketch and drawing a circle. The pitch diameter is one of the most important features of a gear. It defines where two gears interact with each other and sets the stage for the tooth profile itself. So we're going to drive this with a dimension. Now you could calculate the pitch diameter manually on your own and enter the value here, but SolidWorks allows you to enter equations on the fly to solve for this by simply pressing the equals key. When you do this, SolidWorks presents you with a series of file properties and functions you can reference, as well as any global variables you've created. All you need to do is select them and SolidWorks will include them in the equation. Likewise, you can enter any operators by using the asterisk for multiplication or plus, minus in division, etc. Just make sure to keep spaces around them to keep the syntax correct. In the case of the metric module system, the pitch diameter is the module times the number of teeth. Pressing this green checkbox will allow you to validate your equation format to make sure you solved it properly, and we can see that it's 50mm. Pressing OK, we can see that the dimension now has a red E in front of it, signifying that this value is being controlled by an equation. This will be important as we continue on. Let's move next to establishing the outside diameter. This value can now be derived one of a few ways. The first way would be to specify the addendum of the gear. Now in the case of the metric module system, this would be the module value itself, which you could type in manually, but if you want to add intelligence, like I previously mentioned, we can use an equation and drive that from the module value. But in this case, I'm going to cancel this altogether and look at a slightly more complex equation. The full equation for calculating the outside diameter contains order of operations, and Solidworks allows us to incorporate this using parentheses just like in traditional algebra. When we start with a parenthesis, we can start generating our equation again using global variables. But this time, I'm going to go ahead and start typing the name of a known global variable. And you can see that Solidworks filters this list, making it easy to select them. Always select this from the list, however. That way, Solidworks will always add the proper quotes around the variable name. In this case, we want to add 2 to the value of number of teeth and enclose this in parentheses. We then want to take the solved value and multiply this by the module. Again, I can simply start typing the value I'm looking for and select it from the list. Again, the green checkbox allows you to validate the syntax of your equation, and it shows you the solved value. Now, if we want to validate our results, we could use the measurement tool in SolidWorks and select the 2 circles, and sure enough, the value is 2 millimeters like we expected. The last value we want to capture is going to be the root diameter, and in our case, we're going to be incorporating clearance. So we're going to do this by solving for the whole depth, from the outside diameter to the root diameter itself. Now, if you wanted to design this line to line, for instance, you could double the addendum value, but as I mentioned, we want to incorporate clearance. So we're going to use a slightly more complex equation. We're going to multiply the module value by one of 2 values, and by that I mean when the module value is finer than 1.25, we want to multiply this by 2.4. When it's equal to or coarser than 1.25, we want to multiply this value by 2.25. So how do we do this in an equation? Well, SolidWorks offers conditional statements underneath functions. In this case, we'll use an if statement. If you're not familiar with if statements from programming or Microsoft Excel, they allow you to evaluate a statement. In this case, we want to evaluate if module is equal than or greater to, and I had mentioned 1.25. When SolidWorks evaluates this, behind a comma, you can choose a value to use if that statement is true. And in this case, if that statement is true, we want to multiply it by 2.25. Separating with yet another comma, you can enter a value for if the first statement is false, in this case 2.4. Again, using the green checkbox will validate the syntax of your equation, and pressing OK will finish it. So we've generated our overall circles here, and you can see that every value is driven by an equation. Keep this in mind as we move along later on and make changes to our design. At this point, I just want to go ahead and extrude this. With a sketch selected, I'm going to choose the extrude command, and you'll notice that because this sketch contains multiple profiles, SolidWorks has enabled selected contours. Selected contours allow you to select just portions of your sketch. Now, we could select each one of these regions, but you can also select the outside diameter to capture that whole circle. I'm then going to right mouse click and choose a mid-plane extrusion type, and I'm simply just going to drag out this value to 20 millimeters and right click to finish it. For good measure, we're going to set the material to make sure our part's more physically or visually appealing. So one of the things I just mentioned is that I used a mid-plane extrusion. This is actually really important. This sets the front plane right down the center of our part. Not as important for creating spur gears, but when we create the helical gear later on, it'll become more apparent. Likewise, the origin is in the center of our part, directly in the center. This gives us the ability to reference that point throughout our design, and this is often an overlooked yet critical part of working in a parametric design tool. But let's go ahead and start on the front plane creating our tooth profile. I'm going to look straight on at this. Because the tooth profile is symmetric, it makes sense to start with a center line right down the middle. Now, what we're going to be creating is not the tooth itself, but rather the cut in between the teeth. And to do this, I'm going to create an arc. And let's go ahead and start by just generating a 3-point arc out here. Now, I want this arc on both sides of the center line, so I can either pre-select them both and choose mirror entities, Or I can select mirror entities first and select the object I want to mirror, and then right mouse click and choose which object to mirror about. Now we need the base circle here. And to do this, we can go into the Feature Manager tree and turn on any sketches we've previously created, and using Convert Entities, select that for reuse. Now you'll notice that if I drag the end of this arc, I can snap it right onto that circle. I'm going to go ahead and hide this sketch or I'm going to toggle off visibility of sketches for right now, but we will come back to that. Now you can see what I've done. I've copied that circle into this sketch, but I don't need the whole thing. So I'm going to go ahead and use trim to clean that up. Likewise, I want this cut to actually extend outside beyond this part. So I'm going to offset this outside edge by 1 millimeter. I'm not going to get into the details of why you want to do this, but oftentimes you want to extend geometry just a little bit beyond your part. This will be a little bit more important when you create the helical gear later on. So I've got the initial cut, but you can see because the geometry is blue, it's very undefined at this point. We need to capture a few other key pieces of information, and I'm going to toggle those sketches back on to talk about one of them. The point in where the pitch circle crosses this arc is a critical point in your design, and it would make sense to capture that. You could do this with a point, but I'm going to do it with a construction line, and as I continue on, you'll see why this becomes important. I'm going to draw a horizontal construction line, and I know it's horizontal because of the little yellow symbol next to my cursor. I want this point to always exist where these two lines intersect. So by holding Control, I can select all the geometry at once and choose the intersect relationship. I'm also going to do the same thing on the other side to make sure that that's symmetric. Now you'll notice what's happened here. My tooth profile has adjusted in an undesirable way. The reality is this arc needs to be tangent to the angle in which it comes out of the center of this circle. So we're going to capture that by using another center line. Center lines are great for construction geometry. Just make sure in this case that you make sure to add the tangent relationship by selecting both pieces of geometry. So one of the first things that we need to capture with this point is what's called the pressure angle. The pressure angle is the angle at which this tooth interacts with the adjacent gear. We can capture this in this sketch by drawing a center line or a construction line from this center line and making it tangent to this face, but also ensuring that it's always coincident to that construction line. Then we can simply add the pressure angle itself, in this case 20 degrees. So a few other pieces of information are missing. You can see that we're able to expand this, though the profile is pretty much holding its own. This is because we need to incorporate the number of teeth into our gear. To do this, we could do a calculation to solve for the cordial width of this cut, but I'm going to do this using some sketch geometry. I'm going to draw a center line that would basically represent where the center of the adjacent tooth to this cut resides, not the adjacent cut. So that means that the distance between this can be calculated because we know the number of teeth. Let's explain with the equation itself. If we were dimensioning the distance from one cut to the next, it would actually be 360 degrees divided by the number of teeth. But in this case, and don't forget to press the equal sign, we only want half that value. So we're going to choose 180 degrees divided by the number of teeth. And basically now, this center line represents the center of the tooth next to this cut. Why is that important? Well, we're going to set the width of our cut to be the same as the width of our tooth. To do this, we're going to draw a center line across where this tooth would exist. We'll establish that this is perpendicular to the center line, and then finally the last piece of the equation is to make these two construction lines equal to each other. As soon as we do that, you'll notice that the sketch is completely defined, and this is signified by that all the geometry is black and nothing is blue. Now, when you're finished with a sketch, you can always go back into the Feature Manager tree and choose to hide it. What we need to do now is we simply need to close this sketch and choose to do a cut, and we'll choose a through all in both directions. Now, one of the things I missed was the fillet that often falls at the bottom of that tooth. I'm going to go ahead and do this with a feature instead. Within the fillet feature, you can actually select any geometry and you can create equations here. In this case, we're going to use the equation of 0.3 times our module value. And again, by typing it in, I quickly filter that list down. When I press OK, Solidworks updates the size and creates the fillet. The last thing we need to do is create a pattern of these teeth. To do this, we'll use circular pattern. We'll select the features we want to pattern, in this case the cut and the fillet, and then we'll go ahead and choose what we want to pattern about. Now I should point out, you can choose many different things here. You can enable the display of temporary axes and choose the axis down the center of the part. You could select a cylindrical edge, or you could select a cylindrical face. Either you choose is okay. I'm just letting you know there's different things you can choose in this case. We do need to specify the number of teeth, and like before, we could statically enter the value, but I'm going to control this with an equation and link this to our global variable we specified earlier, number of teeth. Once the gear is done, all we need to do is create some breaks around here. I'm going to skip this step for now, but I want to dive in and show what we've done with equations so far. If you right-click on the Equations folder and go to Manage Equations, we can now drive this entire gear with these two simple values. For example, if we want to change the number of teeth, I can simply change this to, for instance, 30. Likewise, if we reduce the module size, in this case to 1.5, it'll update as well. Keep in mind, if we reduce this below the 1.25 value down below, it's going to honor that conditional statement that we set when we created the clearance for the root diameter. Now, at this point, we've created a spur gear quite easily. I now want to show how to create a helical gear in much the same manner. And to do this, I'm simply going to delete this cut and any of the child features associated with it. Now, you'll notice when you do this, Solidworks does retain the equations, so it's a good idea to go in here and delete these. The reason it keeps them is you can technically reestablish them later on, but I often find it easier just to recreate them. So to create a helical gear, we need to do a few other things. I'm going to temporarily shut off the visibility of the profile sketch, and I'm going to start a new sketch on the top plane. Within this sketch, I'm going to just simply draw a line that represents our helix angle. And in doing so, I'm going to create a midpoint relationship to the origin. This midpoint relationship ensures that the line always passes through the center and the endpoints stay symmetrical in regards to their distance from the center. All we need to do now is specify the angle. To do this, and because I've kept my origin at the center of the part, I can dimension directly to the right plane and this line and specify the helix angle, in this case 10 degrees. Now, if we go over and look at this sketch, you can see that it resides in the middle of the part. So how are we supposed to use this? Let's close this and take a look by turning back on our sketches. What I actually need is how this angle drapes across this surface up here. And to capture this, we're going to use a projected curve. Within the projected curve command, you can choose the type Sketch on Faces, and you can select any sketch and choose to project it onto any face. What we've done is basically set how that cut should go across our part. Now at this point, you'll see a lot of videos where they try to do things such as twisting the geometry or sweeps, or they'll calculate this, but by using a few simple features, I'm letting Solidworks do the work for me. The last thing we need to do to be able to create a cut loft is we need this profile on the front of the part and on the back of the part. Now I don't want to redraw this profile, so instead I'm going to use an old capability that Solidworks has had for quite a while called derived sketches. Derived sketches allow you to copy a sketch from one place to another and maintain all the geometry. To use it, you simply pre-select the sketch and holding the control key, select the face you want to copy it onto, and then you can go to Insert, Derived Sketch. Likewise, you could use command search to do this, and don't forget to pre-select. I accidentally hit escape there. We're going to type in derived sketch, or start typing it, and command search will present this as an option. When we choose this, Solidworks copies the sketch onto this face, but it's a little bit unique with what it did. You'll notice all the geometry always moves together. What we're going to do in this case is snap the center onto the center of our part. When we go back out, we can see now that all the geometry moves together. What we're going to do with this arc that we created is we're going to select it, and holding the control key, select this common point that passes through and create a pierce relationship. And you can see that that turned the entire sketch black, meaning that it's fully defined. Let's do that again on the back of our part. Again, we're going to pre-select our original sketch. We're going to pre-select the back face, and because derived sketch was the last thing we searched for in command search, I can just simply click the spyglass and choose it again. Now again, I'm going to look at this and I'm going to simply snap this onto the center, and it doesn't look like I got it. If you have trouble with this, you can always pre-select the origin in this point and choose coincident. And then like before, I'm going to select this common point, and holding control, choose the projected curve and add a pierce relationship. I'm then going to exit the sketch. At this point, all we need to do is create our lofted cut. To do this, we're going to simply select each profile. Now it's important to select the profile by the same area in the geometry. Let me explain. I chose this profile near the upper right hand corner. If I select near the opposite corner in the next profile, you can see we'll have a problem. Of course, Solidworks allows you to correct this with these drag handles easily. We then need to select the last profile and simply right mouse click to confirm. Finally, let's re-add those fillets to the bottom of our sketch, and again, we're going to enter the equation module times 0.3, and we'll select the bottom edges of that feature. And just like we did before, we'll create a circular pattern. This time we're going to select the lofted cut in the fillets, and for our pattern direction we'll choose the same face as before and re-enter the equation here for the number of teeth. When we press OK, we can see that the helical gear has been created. We don't need this curve anymore, so you can always go back and hide that. And when we look down at this from a top view, we can see that we have our helical gear. Now, one of the great things we've done, you've already seen with equations, but because we use this projected curve, if, for example, you wanted to make a left-hand version, you could just go back in, modify this sketch, and change this value from 10 to -10. And when you exit the sketch, you can see that the helix has updated in the opposite direction. Hopefully this was a valuable tutorial for you. I know it was a bit long, but it's an often requested and asked for tutorial.